Okay, if you cannot hear me, let me know. Okay, so we are going to start our lecture today. Today we will be, where's my slide? Yeah, we will be discussing the matrices. The matrices are some very critically important facilities for us to do numerical calculations. So we will tell some stories about matrices. There was a homework assignment plan for today, but I decided to also push it back by 1 week, so that next week we will have the third homework assignment, and that will have some information and practices for matrices, along with the catch operations and how to take advantage of catch. Yeah. So I think you can all hear me. Let us do a very quick review of what we have gone through. Well, this semester we did have two off days on Mondays, so we didn't manage to have lectures on 20th September and 11th October. So we are a little bit slow on schedule. That could give you a feeling that the materials for this course is kind of in the not so difficult regime. Well, that is not untrue, I think, because before the midterm examination, there are 6 lectures, 6 or 7. And the contents for those lectures are mainly to review what you already learned during undergrad. And if you are an undergrad, yeah, I think everybody is muted. Let me try to do that again so that we do not have interference. Where we were, it's progress, right? Yeah, so we were reviewing from the first week to the 8th week. We have 6 lectures. They are to review what you already knew or learned during the undergrad, including basic software engineering and basic programming languages of Python and C++ and computer architecture. So from this lecture, the 4th one, we will start with the contiguous array of matrices, then introduce what we usually will use for the advanced facilities in our computers. Most of the time that we write programs treating our computers as a model that is fostered by the programming language. But if we want to write a numerical software for numerical calculation, we actually need to think more about how the real circuit works. So that is why today we are going to talk about matrices, because it is just a bunch of data of the same data type, have the same look and feel, and packed together contiguously in memory. Then we process them. That's the fundamental of using the hardware in an efficient way. And our system or applications requires us to design and implement systems that runs very fast. So we need to know the high-level abstract software structure as well as the low-level hardware constraints or design so that we can write fast code while retain a good architecture of our system for maintenance and all those features we are to develop. So some of us have already started the project proposal, and during the conversation on GitHub, I try my best to tell you that we need to write very fast code, and your design needs to reflect that you are to write very fast code. That is not easy, so that we need from during late September to early November, we have more than 1 month for you to develop your proposal. So roughly, I think a third of the class has been started the proposal, and we have been in discussions, and that is good. That also means that there are like almost 20 people that have not started the proposal or have not posted for review. And I am not able to have conversations with you about what you think about your proposal. So please move faster. We are like 2 or maybe a little bit more than 2 weeks away before our proposal due. And I hope that you still have a little bit of time to make preparation for the midterm examination. So I wouldn't want to have the proposal due at the same time as our midterm. So we have roughly 2 weeks. And using 2 weeks to write something that can be executed for 2 months is already very challenging. So please write up something and try to post it. So if each of you write something on every day, it will take me like 1 or 2 hours to review a proposal every day until the proposal due. And you know, that is actually a lot of time from a full-time engineer. So I cannot promise that I can thoroughly review the proposal from all of you. I will do my best. But please make that happen sooner than later, so that your proposal and your plan will get a chance for the feedback from me, and you have a better chance to have a good execution after the midterm. Okay. So let's go back to our matrices. And today, after running through the materials for the matrix operations, I would like to invite some of you to talk a little bit about what you want to do for the term project. You can think about what you want to say to the class and to me. I want you to have a conversational expression using Zoom to every one of us. And we can do a public discussion about your project. It is okay if you already have a proposal written. You can still talk about it. So all the people in the class will know what you want to do. That will benefit everyone. It is also okay if you have not written a proposal. You can just throw your ideas to the whole class, and we can have still have some discussions, and hopefully to help you to have a better understanding. Okay, so let's get started. Our matrices are our fundamental tools. It has been so for like maybe 60 or 70 years. It's been a long time that we are using matrices to do numerical calculations. Some of the most famous numerical libraries are working around or working for our matrices. Most of them are the linear algebra libraries. So you probably have heard about these basic linear algebra subprograms and linear algebra packages. I think we can click, yeah. This is an ancient web page, and LAPACK is not a lot better. They are both ancient web pages. I think this LAPACK was developed like in the 80s, 1980s, and BLAS was probably also developed around 1980s or 90s. Okay, I can't remember since when we have those linear algebra libraries. They were initially libraries. Okay, initially they were just some Fortran code, and people are writing them and post them online. So they are not the first invention of the linear algebra libraries. Before BLAS and LAPACK, there were a lot of linear algebra libraries. But BLAS and LAPACK were kind of organize all those programs and propose a good implementation as well as an interface. So nowadays, BLAS and LAPACK are no longer just libraries. They are kind of the de facto interface to linear algebra libraries. So there are many implementations for BLAS and LAPACK. The two web pages that you saw were the original implementation, and or we can say they are the reference implementation written in Fortran. And they can still be used right now. You get a Fortran compiler and compile it, and it will run. But there are more vendor-provided libraries that allows us to call and to get the fastest performance on each of the hardware platform. Okay. These are some famous implementation, including Intel's math kernel library and Apple's Vector. So I wonder, have you used BLAS or LAPACK before? If you haven't heard about that, of course you didn't use it. Oops, where is my chat window? Okay. So let me start a poll in Telegram. Okay. A poll is posted in Telegram. So if you have time, I would like to know how, what's your answer? Have you used either or both of the libraries before? If you haven't heard about them, of course you haven't, you probably won't use it. Okay, let's start with the basic linear algebra subroutines. So it has a naming convention, which is pretty much kept compressed. In numerical code, you may see a lot of people writing code like this. So the convention here is there is a character denoting what kind of numerical type, variable type that we are using. And where is my window? Okay, so this is type information. S means single precision real number, and double precision using D. There are two other characters. Well, C is not for character, but for complex number. And zeta means a double precision complex number. So in the classroom for this course, we pretty much do not use complex number. Complex number are very useful, but the use of complex number have some ambiguity about how you define the data type of the complex number. So I would like to save the complexity from you. And single and double precision are both very useful in numerical calculation. Choice of the types are not easy to make. Sometimes that you will need to change your choice of type after you have implementation. And sometimes that you actually need to allow both, just like how BLAST is working, that it needs use a character to denote what is the type of the data. And this is an example of the BLAST function. Swap means swapping two vectors of the single precision real number. So that will lead to our further introduction of our BLAST subroutine. There are 3 levels of BLAST function. The first one, the lower level, is for vector operation. This vector is a mathematical vector. It actually works like the C++ standard vector, but the standard vector is more like data type inspired by the mathematical vector. And this BLAST vector is really mathematical vectors. But in BLAST, that the vector is usually fixed size. You cannot change the length of the vector as you can with standard vector. So it is an array. This BLAST vector is an array having all the elements stored contiguously in memory. Basically, just an array of contiguous data. And here are, in addition to the swap function, here are some other helpers to do the vector operations. This S, AX, PY means A as a scalar constant, multiply by X vector, then plus or make addition of another vector Y. Then store the result in the vector input vector Y. So this interface itself, well, if you are familiar with software engineering, you know this kind of operation has side effect, right? We have an input Y, and we write our data back to the input vector Y. The reason is also a trait for a lot of numerical codes that we tend to minimize the use of memory buffer. Of course, we are able to create another buffer, say Y prime at the left-hand side, and put the data of Y back into, keep the input vector Y intact. then put the result, the whole result, in the new buffer y prime. But we still like this this format that has a side effect. The reason is that if we want to have this y input intact, using this interface, we can copy y before we do the operation. Then call saxty. Then the y will contain y prime. Then we still have our input intact while we are not using additional memory buffer. Well, not more memory buffer, right? But if we really want to discard our input y, this interface will not create a memory buffer. And later we will see that allocating memory is a very expensive thing that we try to minimize, if not eliminate. Okay, there will be a whole lecture here. In mid-November, we will have a whole lecture to talk about how do you manage the memory. Okay, so we will talk about it, and that is very important. So we have another function called a dot. This is actually a very simple thing. It's simpler than our axpy. It just multiply each of the elements in the two vectors together. And I think I can't remember it creating a new buffer or just storing either of them, probably storing y. Okay, and the third example is the square root. Sorry, the Euclidean norm of a vector, but it basically calculate the square and take a square root. So after the calculation, you always get the positive number of your vector. Sorry, I think this formulation is not. Oh, it's correct. Sorry. Yeah. So after calculating the interior inner product, we will have a scalar, and we take a square root of the value. So that is the Euclidean norm of the vector. We usually, when we are talking about Euclidean norm, we usually are thinking that we are doing some geometry, and we are in 2 or 3 dimension spaces. In that case, this function is not of a lot of use. It is particularly useful when you are doing norm calculation for a very high dimension space, like 10,000 or maybe 100,000, something like that. Then calling a helper will make more sense. If you are doing like 2D or 3D geometric operation and you want to know the Euclidean norm, it's actually more efficient to just spell it out to have x times x plus y times y, then take the square root. Compiler will be able to generate faster instructions. So that's the first level blast. And let me pause and see how many have responded our. Oh, we have only 2 votes. Oh, you are not doing a lot of poll in the Telegram. That's okay. Oh, probably it's because that I forgot to add an option that you have not used them, right? That probably explains why I got only 2 votes for that. So let me assume that you probably haven't used the BLAST or LabPACK very frequently before. Okay, good. So that makes sense for me to continue introduce the level 2 and level 3. There are 3 levels. So the level 2 is matrix vector operation. So in those operations, there's always a matrix and a vector. like this general, I think this general equation matrix and vector, or general, I can't remember what E denote for. Okay. So when you want to memorize those BLAST or LAPACK subroutines, actually it's kind of difficult for you to understand what each character means. When you see M and V, you probably can see that they are matrix or vector, but other characters are some hard to remember acronym. It probably doesn't worth the time to try to understand them. Just memorize them. Okay, so here I got matrix A and an input vector X and another input vector Y, and an input coefficient, scalar coefficient alpha, and another for beta. So in this formulation, I got a lot of calculations happening. But most of the time that what we really want is just this matrix A times vector X. Then you have Y to be 0, and alpha to be unity, and beta to be either unity or 0. Then you recover this. Okay. You will say that may incur some overhead for this alpha and beta calculation, right? That is true. But the multiplication by unity usually does not take a lot of time. And what takes time is this matrix vector calculation. So this guy actually is one, not order. It's the time complexity of this scalar multiplication is big O n, I think. And this guy is n squared. So we usually can just discard this multiplication coefficient overhead. Okay, so this is one. Treat this matrix A as full dense matrix that you do not really know what is the content inside the matrix. So you have to visit each of the elements. And GBNV is a banded matrix vector multiplication that has an assumption in the matrix M or A, sorry, that the elements inside the matrix is banded. It's like 3 banded or 5 banded. So it's banded along the diagonal. Of course, then in this, using this SGBNV will not store a full matrix so that the subroutine knows where to get the banded information. And all the off diagonal elements are trivial. You don't need to do calculation. Okay, the third example is for the symmetric matrix. So A still is a full matrix, but we know it is symmetric. So you can either store the lower left half of the matrix or the upper right half of the matrix. And the subroutine will take that into account and do the calculation, which is faster than SGBNV. Okay. Then you may guess the third level of BLAST is the matrix application. Okay. So we will have more discussion about how to do matrix operation later. So this is pretty much what I want to say about this BLAST. Do you have any questions about BLAST? Right. Good. Then we will skip LAPACK because I put LAPACK in the latter half of this class today. I want to first talk about how to implement the BLAST subroutines. We start with our vector, which is just 1D arrays. This is one way for us to represent our vector in 1D array. We declare a variable with a number of elements. So these two statements will tell the compiler, hey, say, on the stack of this function, give me 5 double precision floating points and put them together. Because it is on stack, so we are not using any dynamic allocation. Then I know on stack I can have 5 of the double precision, and I can initialize them like this. I have all the values. Then I can use the bracket symbol to access my element, just like this. Very simple, right? This is how we can store vector in the memory. But remember that we are keep those vectors on stack. And you cannot keep a lot of data on stack, right? Otherwise the stack will overflow. But this is a very fast way for us to process our vector, this plain old data arrays. Then we store the matrices as 2-dimensional arrays. Okay, this is what C and C++ support. Most of the time, it only works for on stack. That's why we talked about stack in the beginning. So here we declare, and remind you that I cannot emphasize this more. In almost all mathematical books that you see all the index notation to start by 1, you need to translate that into zero-based index in mind, or you, like you always do, I rewrite all those index on paper so that I know that the indices are starting from 0 and I do not get confused. Okay, so this is very important. So here we have a 5x5 matrices. So they have elements from A00 to A44. Okay. So here we still declare our matrix on the stack. And this time we can use the double bracket. And that will allow us to access the element, well, just like the 2D array. Just like the real mathematical matrix. And we repeat this this bracket so that we have i's row and j's column in the corresponding field of this plain old data 2D array. Okay, then you can print it out. Okay. This is our matrices. Okay, here comes the dilemma. Can we make the array, especially the 2D arrays, to have variable lengths that in our previous examples that we have the width to be constant expression. So compiler knows this is 5. We are just giving the number 5 a symbol as width, right? And that symbol is only recognized during compile time. It never got into our binary, right? So compiler knows that we are 5x5. But if we declare a function like this and we have the width as a variable passing into the function, no, is it legal? No, it is that the compiler does not know how long as the width. It can no longer know as a 5x5 or 10x10. So internal programming languages, well, it does not know how to treat this variable length array. So, and the different compiler actually treat it in a different way. In G++, the above function actually can compile. G++ has an extension called variable length array. I do not know what exactly G++ does it. But I believe it plays some tricks on stack or something. And in LLVM, it does not support this VLA extension. So it will just throw a compilation error saying it does not know how to create this, how to initialize this matrix pointer using this reinterpret cast. Okay. It doesn't really matter if you use reinterpret cast or not. If you do not use it, G++ will try to do the implicit cast for you. And Clang will still complain about it does not know how to do the cast. Okay. Basically, it needs to know, the compiler needs to know what is the value of width during compile time. Okay. So it is an interesting thing, right? I want to have another poll for you. This time I will make the answer. Oh, it shouldn't be a poll. Let me, because I want to hear from you. What is, have you heard about, sorry. Let me just do a simple yes and no quiz. And if you have heard about it, can you, if you can turn on your voice, you can turn it on. Tell us that what is your use case, or what do you know is the use case of a variable length array? I'll wait for like 1 minute. You can say that in your voice, or you can paste in the chat window, or say that in the Telegram. Oh, I see. Let me get the Telegram. For some reason I cannot find my Telegram link. Why? Okay, so I post the Telegram link again in the chat window, and I haven't got any response about their experience about variable length array. Okay, so let me say a little bit more about my understanding about this. I used to write a lot of variable length array when I still coded in C. That and of course I exclusively use GCC at that time. This variable length array allows me to determine a compact matrix as my computing kernel, and I can generate C and assembly code using this variable length and to do the Jacobian matrix. Those matrices are the Jacobian matrix, and I can calculate the Jacobian matrix in a very efficient way. There are more efficient ways to do the calculation, but at that time, this variable length array is kind of a good balance between high-speed code and good coding productivity. That I can write the code fast. So that's one use case. So a lot of people like to use this variable length array. There should be some problem with this variable length array. It could be a good exercise for you to take a look why people are discouraged from using the variable length array. Okay, I think a lot of articles in the books are saying that this is not as a standard, and it is not a standard for some reasons. Try to avoid this kind of non-standard code from your system. So both has a point. So here I'm not going to judge which one is correct, but I want you to know there are such kind of dilemmatic things that existing in our programming world. Okay, a lot of things in the programming is like this. They are controversial, but when it can get things done, they have a place in our system. All right, let's continue with our matrix access. So how much do we have? Okay. So you still remember that when we're dealing with matrices, we have row major and column major access. So this is a review and explanation about how we use them. So here is a row major matrix. This picture, which we used before, was 2 by 3, 2 rows and 3 columns. So in the row major access, the memory layout is to have each of the row to be ordered consecutively. So we first see the 0th row for the 0 column, then column 1 of the row 0, then column 2, then change the row, and column 0, column 1, column 2. So memory is laying out in this way. Okay, then we extend to other shapes. So here we have a 5 by 5. We have a buffer, and we declare our memory still on stack, but this time we sorry, not on stack. This time we use dynamic allocation. So we allocate an array of 5 by 5. Because here we are using dynamic allocation, you are not restricted on stack. So this width can actually be a variable. So this whole thing can be in a function. You do not need to worry about those variable length arrays because things are dynamic right now. Then we populate our data. Keep in mind that our buffer right now is not a 2D array. We have shown in the previous page that our compiler does not like variable length array for 2D or higher dimensions. So right now we have to use the one-dimensional format of our access. So here we need to know the stride of each of the dimension. Here, I is the row index. So for each of the row, our stride is 5, which is the width. Right? We need to stride for a row from this element to this element. So it will be the number of columns, right? We need to stride over all the columns in this row, right? So for the 0th row, then the whole thing is 0, right? We have only J. J is the number of columns. So we can populate the data like this. This is actually how our 2-dimensional array. This is actually how this thing is working. The only difference is that this in this static form, the calculation part of the calculation can happen during compile time, not in the runtime. But for this loop, well, you still need to do the multiplication because those things are only determined during runtime. So we have this ith row and jth column and have this multiplication, and let's see how it drops. So we have this. We still do the reinterpret cast because we have the constant expression, so we can take advantage of this I and j to show you that it is really working the dynamic allocated memory really can work just like our 2D array. So we populate the data, then we can print it. So first, we print the address. This is part of the simple code posted online. Then we use our old 2D array format syntax to print the element. And you see the data are just like how we are expecting. And you can also print the element in memory, but I do not have enough space, so I didn't show the code here in the slide. You can find the code in the online note. Okay, this is row majoring. So let's come back to Telegram and see what are the poll results. Let me stop. See. Okay, so some of us, let's see. We have Sam heard about variable length array. And almost everyone else have not heard about that before, right? So let me pause a little bit. Information like or experiences like a variable length array are usually learned from practicing. Okay, if you do not write or trace a lot of code, it is reasonable that you haven't heard that before, because like I said, things like this are like controversial, right? So textbooks tend to not mention controversial information, right? Because if saying like I am a writer of a textbook and I'm going to teach students according to the textbook, and I put controversial information in the textbook, then I am kind of shooting myself in the foot, right? I need to do a lot of examination about why this is controversial and do a lot of analysis. And those analyses, well, they are useful, but they are sidetracking the theme of the textbook. So we will all need to learn about those controversial information as we advance in our skills. But we learn that in a rather unorganized way. That is why you might, well, I'm pretty certain that you feel that our course or discussions here in the lecture are not very well organized. They are not, because it's difficult to organize it. I am kind of organizing what I learned during the past 20 or more years for numerical calculation, and try to present them in a course that can be accepted by the university. So yeah, I've done my best, but I still have a lot to improve. But I think this is a format that what we can do for some unorganized programming skill training. Okay, and that is why I emphasize so much about discussions and project proposal and the project execution, because those are the real beef of the course. That how you try to find a direction, do something, and purify your ideas and implementation during the course of development, not the course of the lecture, but the course of development. Okay. So if you have any questions about your programming, well, hopefully about coding for the numerical software, but actually it's okay for you to bring in any question about writing program to the class, to your classmates, to the lecture. I'll try to respond to you, try to use my experience to explain or to analyze what it could mean or what it could look like for your answer. Okay. So that was some unorganized information and the row major access. Here we come to the column major access. So here we are packing memory by column. So we start from column 0, and we have the element 0, 0 and 1, 0 and 0, 1 and 1, 1. So the order of the element are flipped. then our access array becomes a little bit different. Here we have the stride per column. And remember, I intentionally pick a 5 by 5 matrix that is have the same column number and row number. So here we are still using the width. The stride per column is also 5, but we have the index j here because we are striding for each of the column. So we stride over the row. Over all the row in one column. Okay, when we are changing the column index. But keep in mind that in the right-hand side, we are still populating the same data to this column major memory buffer. So we can do a comparison between the column major way and row major way. It is the axis is flipping around. The I and j index are flipping. And this is our execution results. Because our meaning of j and I are flipped, so this POD QD array access need to flip as well. Otherwise, you will get your matrix to be flipped because your access is not in the right order. Okay. You can do some experiment about this, and this is important. And we will have homework assignment to practice this. So we have to learn about this. All right. Then we want to have it's about time. Before we continue to write the class for the matrix, and a little bit more tricks about how we organize the code for the matrix operations, I will pause for like, let's say 4 minutes. Let's come back at 7:55, okay? We take this break and you can, hopefully you have some questions and we can discuss. You can also just take some rest if you do not have a question. Let's do some topics to encourage you to chat. Let me ask some questions on Telegram so that you can think about it and maybe we can have some talk. Chris gave a question asking as a standard vector a kind of variable length array. Strictly speaking, no, because when we are talking about variable length arrays, we are talking about specifically that stack form. This is what we call an array, or C style, a POD, plain old data array. So a variable length array is an array that of variable length, an array on stack, and it is of variable length. Okay, so no, standard vector is not a variable length array. And actually in C++ standard, there is a template called standard array, std double colon array. So even in the C++ template language, a vector is not an array per type, right? But so that is the strict definition of array. However, if you think about the effect, you can say, yeah, well, the standard vector can be used like a variable length array, and you can really change the length of vector, right? So it's much more flexible. That's actually the reason vector is such a very useful container. You know, before vector, there is another template container called val array, value array, and in short, VAL-ARRAY. I think that was invented before this century. And probably nobody uses it anymore. It should be still in the standard library, if I'm correct. Let me try to Google it. Yeah, it's still in the standard library. Okay, so this value array actually works more like the mathematical vector. And the standard vector is, well, it's another thing. Okay. See, there is a formulation that takes the operation to be more or less like our mathematical vector. So yeah, there are distinctions between standard vector and the variable length array. Yeah. When you are writing programs, it does not matter that much to distinguish them. Okay, but when you are optimizing and providing interface to your users, well, those terminology becomes important. Yeah, because you need to let other people know what you are using. This kind of information will be more prominent when we are going after the midterm. So I actually got some feedback from people that, well, from the former students of this course that materials after the midterm becomes much more difficult than before. It's actually kind of surprised me because, in my opinion, well, the lectures before the midterm actually can be tested, so that you actually may prepare for the midterm by just reading or reviewing your previous courses or what the notes that I provided, so that you can take the midterm. And a little bit of information about midterm is that we are going back to classroom next week, right? So that I think I will do the midterm in person. And that will make your life easier. In-person midterm will be a simple midterm. I will not ask you, well, sorry, you are forbidden from using calculator. You need to close book. So what I can test in the midterm is actually pretty limited. And I'm pretty sure that as long as you do a good homework assignment, and have a reasonable review of the computer architecture, and the course note online, it's very difficult for you to earn a bad grade in midterm. Okay, I decided it that way because that those materials are really the background, and as long as you have the concept and find the right information, that is good enough when you are programming. Okay. But the materials after the midterm, it's not so easy to master, and I cover them along with your progress in the projects. That design is intentional. In that way, you will be introduced with those advanced programming concepts, but you may not apply them in your project development. Okay, well, I'm not discouraging you from using them, but it doesn't make sense to learn some new tricks while you're doing a project. You may think about, when you are in the lecture, you can think about how those concepts or skills can be used in your code development, but you are not requested to use them in your project. So I hope those parallel development can help you have a better, a more immersed experience in learning of the skills. Okay, so let's come back to our matrix class. Okay. We are writing C++, so it is natural for us to create a class for matrix. It's not just orthodox, but also very useful. It's one of the best things that C++ offer for numerical calculation, okay? Because we can create a class, or actually class templates, for us to operate those data objects. So this is a simple matrix class. We do not use class so simple like this in real world, but this is a demonstration to you. So we create a constructor and destructor. So we have memory allocation in the constructor and the destructor. Then we overload the operator parentheses, the calling operator, and provide the row and column indices. So, and we can return the buffer. So here we are using the calling operator like an accessor, right? So when we are getting the row and column number and the conversion of this thing, we know that we will return by value. We return this element as this equation and copy to our column. Okay. We intentionally return by value because we know that on our architecture, or most of the architecture that we will do serious computing, a double is 8 byte, and the pointer is also 8 byte. So for a single, for just one element of double precision floating point, it doesn't make sense to return by reference. So we just return the value, and it should be just a movement in the register. It should be very fast. Okay. And we overload the same operator again for the non-const version. But this time, we return the reference, so which is a pointer. Well, that is because that we want to allow user to write to the memory buffer. Okay, so we cannot just return by copy, because that will not allow user to write it back. So this pair of this one method or one function accessor is very useful and allows us to write a beautiful code like this. Okay. This is our operator parentheses. Just copy them from the previous page, and we can populate the data. Our access of, and this is actually the setter. This statement are used in the non-const version of the overload, and I'm assigning the right-hand side value to my matrix. Okay, then you can write some program to see. Let me see if I have the example. No. Okay, but you can write some simple code like I posted online and print the content of the matrix. Okay. I like it. Hope you like it too. And this introduces another tricks that we can play. Well, this is a trick that, sorry, I should say this is a simple version of the trick. In practice, that we actually don't use this kind of trick. But in the example that I'm showing you and in your homework assignment, you can probably use it. This is just to try to build your concept about how to do the matrix operation. First, we recall what is a transpose, right? Say we have a matrix A and it's laying out like this. It's a M row by N column matrix, right? N rows and N columns. So N is in the second index, M is in the first index. And we transpose it. So we have a transpose matrix. What does it do? It actually flips the column and row index. So right now we have an N by M matrix. We have N rows and M. N rows and M column. Okay, yeah, it's kind of tricky. Right? So I am keeping the indexes the same in the two matrix so that you know the value in each location have a mapping, right? Here to here, here to here. They have a 1-to-1 mapping. I probably should write some arrows so that to show you their relation. Here is A12, it becomes A12 here. So it's INJ flipping. So if we know transpose is working like this, right? This is a mathematical form. It is mathematical transpose. To realize that in our computer, we can do the same trick. So here, our operator parentheses calling another helper called index to calculate the index. And we keep a new, here, we keep a new bit in our class saying, am I transposed or not? By default, it is false. But if it is transposed, then we swap this number of row and number of columns so that my shape will get corrected. Then I recorded my transpose status. If I am transposed, then my striding will be going to the column number, not the row number. In the normal mode, I stride per row over all the columns in it. Okay. So this trick uses a runtime check in my index, and it is a major reason. One of the major reasons that we do not use this transpose technique in production code. It is not so good for performance. However, if you really measure the performance, you probably cannot notice a thing. Because modern CPUs actually optimize this conditional branch pretty well. And once you set a transpose bit, for all the operations afterwards, this evaluation will always go one of the branch. it does not flipping. Sorry, it's not switching between true and false, right? So the CPU's branch prediction can predict this behavior pretty well. So this if and else will almost take no effect in the code like this. Okay. But we still want to avoid that because that is not so good for other hardware. Like if you are coding on GPU, and then this will be a pretty bad thing. Okay, we don't want this. Okay, so this is our matrix class. We will use this matrix class to have more discussions about how we write matrix code. Let's go with matrix vector and matrix multiplication. We will use naive implementation or algorithm to say what we want to do. And I'm going to say a little bit about how we turn equations into code. I have been working with a lot of scientists and engineers. And so in my anecdotal survey or statistics, everyone I met who are doing scientific research and coding, they cannot do that in the same time, including myself. I know how to derive equations. I can invent some theories. And I also know how to code. I can put together some lecture notes for you, and I can do architecture. And I can trace code and do debug for memory error. So I have a lot of skills in code development and software engineering. But I cannot do them at once. When I am deriving equations, I have to focus on the equations, not the code. When I'm writing code, I need to read the equation as is. I cannot write code and try to fix my derivation in the same time. So it is amazing to me that, from the superficial view, mathematics and computer program have a lot in common. But somehow your mind is working very differently when you are doing math and doing program. Okay, like I rarely go Google when I am deriving equations. Well, I may do some Googling and see if my understanding of a subject is correct. But when I sit down and trying to derive equation, I need to sit there for like 30 minutes or an hour just to check up if my derivation is adding up. Then I can go back to read some materials. Okay. But when you are programming, actually it is not uncommon for you to go to your browser and see what people are saying on Stack Overflow and copy the code down to your text editor, then modify it so that it fits into your applications, right? Well, I'm not saying that you should go copy Stack Overflow, but I'm saying that it is, you will find yourself doing that all the time. It is something that actually fit your code and flow. But again, not everything can be copied from Stack Overflow. So here, I'm showing from our matrix and vector mathematical format to the index format. Because when you are dealing with a lot of data, most likely that you put them in arrays, vectors and matrices. And you will need to know the indices in them. Okay, so we start with our y equal to a times x. Then we can write it in the index summation form. We know the column vector y have an index I. And in the right-hand side, we can write our column vector X using index J. And this matrix A times X can be written in this summation form like this. And the result will still be a column vector of, well, the result of A times J, as A times X. Okay. Then we can use, it's common for us to drop the summation by using instant summation convention. This convention is saying that in each of the term, when you have the repeating indices, you are summing over them. Okay. So on the left-hand side, you have the index I. On the right-hand side, because your J index is summation, is summed together, then you only left index I. Okay. And the same applies to a transpose. Okay, so we have Y prime and use J as the indices, and X prime I using I as the indices. Then we have, this is the formula for the transpose. Okay, let's see how the code is working. After we have that, this formulation, then the kernel of this summation becomes trivial, right? So this is almost, it's actually the literal translation of this thing, right? The only difference is that this is a summation, right? And we have a temporary variable v starting from 0 to accumulate this summation. Then we assign the return vector element I to the sum, the variable value v. Okay. Okay. And here we have a little bit confusion. That is, we are using one-based index. But you will find that this does not pose a challenge here, because in the inner loop, it has only single offset. To me, it is easy to understand. But if you are not familiar with this kind of thing, you can, in your formulation, you can offset this value by 1. Okay, it's up to you. Okay. And I see a question from Sam. Sam was asking that whether or not BLAS or LabPack or other libraries support missing values. Let me guess what you mean by missing values. Are you saying that in some location in the matrices, there are values that is not a number? If you are talking about not a number, then the answer is no. BLAS and LabPack does not handle not a number. I think you will get not a number as a result. I think everything times not a number is another number. Okay, so missing values are not like that, are not supported. But if your missing value is 0, the trivial value, well, of course it is supported. A trivial value times everything is still trivial. So it just multiply by 0 and give you then 0. And that's the normal arithmetic. Sorry, pronounced incorrectly. I mean arithmetic. Okay. So Sam, if I didn't answer your question, you can let me know. Okay. So this is the naive matrix vector multiplication code. So a one-to-one mapping. I love one-to-one mapping a lot. Okay. Then let's try with a task. We have matrix vector multiplication by using a square matrix. And we test it using an identity matrix, which have only the diagonal value, and diagonal value is unity. So anything B times the identity matrix will become B. So result Y will be just B. Okay, that is how the identity matrix work. Okay, so we populate this identity matrix and do the multiplication. Oh, this is the multiplication operator here because we overload that operator for our matrix class. Okay, so we can write a code like this. So we have this multiplication happen and print the results, and we see that our result is recovering our input vector B. Okay. Keep in mind that BLAST is using a different interface than this. Okay, so this is more like this is just like an example. Okay, then we can try to multiply with a rectangular matrix. Our matrix may not be square, right? Although we were talking about square matrices until this point, but it can deal with any matrices. Oops. So here is the formula. We have a matrix of 2 rows and 3 columns. Okay, then let's do a population. So our matrix is 1, 2, 3, 4, 5, 6. Our vector is 1, 2, 3. So keep in mind that the column number need to match the row number of the second matrix. So this is 2 by 3 and 3 by 1. So the right hand side is will be turned into a column vector of 2 by 1. Okay. So we keep using the term column vector because in the format here, you see there are 2 rows and 1 column, 3 rows and 1 column, right? So it's actually a single column matrix, right? Our vector is a single column matrix. So that's why we call it a column vector. So in the same way, there are actually vector defined as a row vector. Okay, not a column vector. It's a single row. We will see that later when we are dealing with the eigenvalue problems. Okay, we initialize the vector and do the multiplication. I think you can do that by using your mind. It's 1 times 1 plus 2 times 2 plus 3 times 3, so it should be 14. The same happens to 4, 5, 6, and it's 32. Okay, then we get the answer. Okay, here is the code to do the multiplication. Okay, and we can also deal with transpose matrix. So the result will be the same, and you can see that the memory buffer is column major. Okay, we have column here, we got column here, and our matrix is a column by column. The implementation of the multiplication was here, right? We are using our operator parentheses to access the element. So it doesn't really matter what is the majoring of our memory buffer. We always are getting the correct index by using our operator parentheses. Yeah. So we got the 3 by 1 column vector with the value here. Okay. This is to show that we can actually use the matrix to change the majoring. See, here we copy our matrix to a new one. This operation respect our transpose bit, but the newly created matrix is row major again, like here. Yeah, matrix A buffer here. A is the same matrix, but the buffer is changed back to row major. And we do the multiplication and recover the same value because the algorithm is the same. We can compare with our transposed matrix vector multiplication. The buffer is column major. and this thing is result is still the same. Okay, this is our assignment operator. So we get another matrix, and we will do the data copy, do some vicinity check, and set the buffer size, and do the value copy. We are using our operator parentheses so that we get the correct transpose bit. Correct element, regardless of the transpose bit. Okay. So that is our matrix vector multiplication. Then we talk about matrix multiplication. So here is this thing is one of the model problem of high performance computing because it is pretty complex. It is usually an n-cube algorithm. When we're talking about the naive algorithm, it is n-cube. But even if you are very smart, it's actually not much better than n-cube. So we have three matrices, A, B, and C. So we want to get the result of matrix A times matrix B. So it's n by n and n by l. And your result will be n by l. Your column of A and the row of B will be summed together. And you need three different memory buffers for this operation. You cannot reuse any of the buffers of A, B, and C. You need three distinct buffers, two for the input and the third for the output. So this is very different from our vector operations. So the same flow of simplification, then you get a simple, let's say, simple formula for the multiplication. Well, in real world, of course, you will run into formula much more complex. Let me give you an example about my previous work. Let's see. What did I have? Okay, this is matrix vector form of the solving the Euler equation. So there will be some Jacobian matrices like what I mentioned, and I'm showing you what is the Jacobian matrix looks like. Okay. Oh, I didn't have it spelled out. Okay, here is the formula in the matrix vector form. And this A matrix are my Jacobian matrices. I have three of them because I'm going in the three-dimensional calculation. So I need three Jacobian matrices. And there are a lot of zeros in the Jacobian matrices, like here. I listed all the zeros here, and there are several unities in the Jacobian matrices. So because they are 0 or 1, I do not need to change them every time I do the calculation. But there are a lot of elements, they are variables during my calculations, so that I leave the component here. Okay, and for the second Jacobian, the value are like this. For the third one, the value are like this. So they are pretty complicated. Okay, and there are a lot of either constants or variable, and I left all the meanings of those variables here. Okay. So your formulation may go very complex if you are dealing with some real problems. But this is the simplest form of a formulation that you can write. Let's go with the naive algorithm for the matrix multiplication. Okay, so this is a kernel. Well, actually, this line is a kernel, but we do have a three-level nested loop. That's why it is n-cube. We need to iterate through all those elements in the matrices, and our matrices are rectangular, so it is not exactly n cubed because we actually have three length variables n and l, right? But let's assume that we are dealing with square matrices, okay? And it is often that we are dealing with square matrices, so that time complexity becomes n. Okay. So the kernel of the naive implementation is simply just summing over all the elements of each of the column of the specific row of the first matrix and each of the rows in the certain column in the specific in the second matrix. Okay, algorithm is very simple. So you can do a simple verification, like we have, where is our matrix? All right, I forgot to put the mathematical form, but let's read the code and see what is the math. So we have the first matrix, 2 by 3 matrix, 2 rows and 3 columns. And we have the second matrix, B, it is 3 by 2, 3 rows and 2 columns. Then we multiply 1 and 2 to the third. So we have A, B, and C printed. Okay, 2 by 3, 3 by 2, and 2 by 2 is the results. So we can do a simple verification. We have 1 times 1 plus 2 times 3, and the 3 times 5. So it's 1 is 7, 22. Okay. So we got the same results. We got the correct results. Okay, this is the naive implementation. But there is a famous algorithm called the Strasson's algorithm. That is faster, but it is much more difficult to implement. And the asymptotic time complexity is big O n to the power of 2.8. So it is not much better. Our naive implementation is n cubed, right? But the Strasson, the better algorithm is n to the power of 2.8. It's roughly n cubed. So not a lot of people choose to implement that. In the next lecture, we will talk about how to use cache. And by using cache, we actually can obtain very good speed up of this matrix multiplication. In that scenario, we will start to consider whether or not we use this more advanced algorithm to make our performance to be even better. Okay, but if we are doing a naive implementation like this, then turning that into an advanced algorithm probably does not buy you a lot of runtime. Yeah. Sorry, I was talking conservatively. It actually doesn't buy you much runtime. But it's good for you to take a look about this article. I think you can access it through the university network. All right. A little bit more information about the matrix multiplication. So this linear algebra essential operation is not commutative. So be very careful when you are dealing with code like this. You have a 2 by 3 and 3 by 2 matrix like we had before. It will give you a 2 by 2 matrix. But if you change the order of the multiplication, it will give you a 3 by 3. Okay. It is simple. It is a simple demonstration that you cannot make them commutative. It doesn't really matter if your A and B are square matrix. They are still not commutative. Okay. It is not about the shape, but the shape is very descriptive about why you cannot make them commutative. You can go back to read your linear algebra textbook to learn why they are not. But keep that in mind. A lot of things that you read from the formula or equations may not be so innocent as they seem. So always think about what you are doing before you write the code. Otherwise, you can make a mistake. Okay, and this is a good verification about your the code you are writing. In your project, you probably won't write a matrix operation like this, but you will have some equations or some algorithms to implement, right? You better provide some verification problems that you know your code is solving the right problems or equations. So that will be a very important step in your testing process. Okay. Any questions? If not, we are moving forward to LAPACK. Okay. In the you can ask me any question when you want. Okay. I have like 10 pages for some basic operation, for some basic helpers in LAPACK. I'm not going to give you a training for how to use LAPACK. I'm give you an impression about what is the code look like when you are writing code for by using LAPACK. Okay. There's a difference because training to use LAPACK or training to use a library is something that I don't really want you to learn. In my expectation, you are supposed to be able to learn how to use libraries by yourself. So ideally, I should not cover anything like the code I'm showing here. You should learn it by yourself. However, the other reality is not a lot of people are used to write or read the code for numerical calculation. Like I explained in the beginning for BLAST. BLAST interface is designed to reuse the buffer for input. Reuse the input buffer for output, right? Which is a practice that most of the software engineering materials articles are discouraging you from doing. And we should not reuse a buffer, which result into some side effect that is hard to predict, right? But our numerical libraries are designed to violate that very rules of software engineering. Okay. Actually, that engineering practice is pretty good. But the software engineering principle of buffer segregation is also very good. So here I'm not able to give you a simple guideline about which one is a good way, because there is not such an answer. And sometimes sharing buffer is good. Sometimes segregating buffers is good. You need to decide yourself. I also heard about a story. It's not about numerical programming. It's about is an anecdote in LLVM community that some people like to use reference. LLVM is developed by using C++, so it intensively uses reference. So they decided to use a reference in the function signature to support the returning argument, which is the argument that is used for output rather than input. Right? We do have that kind of convention in some libraries. Then some other people say it is not good to use reference as an output variable. It is not easy to read. So they find that module and replace all those output reference to be output pointers. Pretty much they are the same, right? Because compiler will change the reference into pointers, and the generated machine code should be exactly the same. But the syntax in C++ to operate reference and the pointers are different. So you have to change the source code to change from reference to pointer. Okay. Then the original group of people think they should use reference. Then they change it back. Okay, that is silly, right? Because that is merely a convention. And there is no definite answer about which one is good. It actually depends on the group of people who are maintaining that module. So as long as they can come to an agreement, then that is a good practice, right? In the end of the day, actually using reusing output variable is a bad idea anyway. Okay, and they have already chosen to use the output variable, so it is what it is. Okay, so arguing about how to support the output argument is such a minor thing that we don't need to spend time on. And in writing program, especially writing program with other people, there are a lot of scenarios like this to happen. Okay. Let me give you another poll. The question, I'm typing the question. Oops. Oops. Sorry to keep you waiting. Okay. So this is a question about whether or not you have been in an argument about coding convention, how your style of code should be in a software project. You might be participating that argument, expressing your opinion, or you might be the one that initiated that argument or fight, squirrel, or it never happened to you. It's probably because you don't care about it, or you haven't been in a software project that is large enough to have a coding convention. Okay, I'd like to know what's your experience in this one. My expectation was that you probably haven't been in any argument like this. So surprise me if you can. Because in joining in a software project involving many people, so many that you need a coding convention actually takes a lot of energies from you. Like in your college, you will be asked to do some competitive programming. There are some kind of tasks to show you that you can do some of the fundamental algorithm implementation and some program that you are developing to fit some goals, some kind of leak code kind of stuff. That is not real programming. Sorry, I mean, that is not the programming for real world problems. Those are more like, you know, I'm from mechanical engineering, right? So I learned about mechanics. In mechanics, we always have a lot of model problems. That is like some rectangular pictures that say this is a system, there is another block, and something is flowing from this block to that block. We abstract and generalize the world into some simpler problems. And the LeetCode style, the competitive programming, are that kind of model problems. But in the real world, the boundaries of your system is not defined as clearly as the model problems that you are receiving. You need to define yourself. What does the system look like? Okay, so the training you received in doing LeetCode is actually to give you some building block. And when you are working on the building blocks, you rarely need to talk to people, right? Like if you are really in an interview, which your interviewer asks you to do some blackboard or whiteboard programming, you will only talk to that guy at most, or that guy will probably even ask you to do that, do the problem alone by yourself without talking. So you are not in a discussion. You will be more like to pull the information from your head and at most have a discussion with the other party. But in a teamwork environment for software development, you need to talk to many people. Talking becomes a primary activity in your work, in your program work. Okay, it is not optional. So in the end of the day, if you do not ask questions and learn from your project leader or your colleagues who have worked on the problem for like a year or two, then how are you gonna to understand what is the problem? Okay, you might thought, hey, that go to find a book stating what the problem is. Well, if your problem in work has been written in a book, then it's already a proof that the work is highly replaceable, right? Because what has to be done in your job is already written in a book. So everybody reading the book can do your job. How more replaceable can that be? And we do not want to work a job that is highly replaceable, right? We want to be unique. We want to solve unique problems. That is good for your career. Then you need to deal with problems that are hard to be defined and has a lot of controversial information in it, something like our LAPACK. Okay. But of course, LAPACK is not the only problem we have. So here, let's solve a linear system. We have 3 equations and 3 variables. So we should be able, and we know those equations are linearly independent. So we should be able to solve for an exact solution for those variables. Then we turn this problem into a linear system like this. Sorry, linear algebra like this. When you are familiar with problems, this kind of problems, you know this can be directly cast into this form. So our matrix A and B and X are all populated. We can write a program to populate the data and use DGESV, D for double precision. So the first character is following the same convention as we had with BLAS. Okay. The prefixing LAPACK E underscore is the interface for LAPACK in C. Okay, so this is the C interface. Recall that our LAPACK was developed in Fortran. So Fortran has a different calling convention than C. So we need a wrapper to make those Fortran symbols to be available in our C program. And here is a C++ program. And we need to prepare a lot of input for LabPack. Each time when I need to use LabPack, I need to go back to the manual and there's the example code to understand what is our what is our field's meaning. It's hard to remember. But the essential is that first specify, am I using row major or column major for my matrix? Okay, it's an integer for designating the majoring. And we specify, well, here is a square matrix. So we only specify the number of n, the rank of our system. And we need to know how many columns do we have in the right-hand side. So it is a B vector number of columns. There can be multiple vectors to be solved in the same time. That's why we need this number of columns. Then we send the pointer to the matrix, to our function, to the LabPack function. Then we send the leading dimension of our matrix, which is the number of columns. Then we send another buffer we allocated here for pivoting. The pivoting is a value used during the calculation of the internal. So it is yet another what we call leakage of abstraction. So it is actually telling you some internal information for the GESB implementation. Then we send the number of, we send the right-hand side vector into the GESB function. Then again, the B leading convention, leading dimension. There's a number of column too. Yeah. Here is the leading convention for row major matrix actually is the trailing dimension. Yeah. It will be number of row when you are going with column major, which I will. Do I have it? Yeah. Okay, the results is here. Okay, the first column of B, well, is the value that I have a specific design, so that it will give us a very beautiful integer solution. And the second column is some number that I just randomly changed. So the solution will not be so beautiful, but both are correct solution to the problems. Okay, you can do some verification by yourself. Okay. And when you are doing column major, you have the major number to change to this symbol. Those are the number of rows changed, like here, leading dimension of matrix A and leading dimension of matrix B or vector B. Okay. And the solution is the same. Okay. So there are some materials in the Intel website as a documentation for MKL. I find that that probably is the best LabPack documentation that you can access, no matter it's online or offline. So you can go take a look when you need to use LabPack, and most likely that you will use MKL for by calling LabPack. So reading the MKL documentation, well, makes sense anyway. Okay, so this is the first model problem of our LabPack. The second, no, not the second one. What I want to say here, okay? Okay, we've pretty much covered that. Thanks for myself for the reminder. Then we want to talk about the eigenvalue problem. So in LAPACK, the eigenvalue problem and singular value decomposition are kind of cousins. They use similar interfaces. We go with the eigenvalue problems to begin with. That I don't know how. Oh, I want to have another poll. Whether or not you remember what is eigenvalue problem. Okay. In numerical analysis, problems like the linear system solution, eigenvalue problems, or single value decomposition are considered fundamental. That we expect everyone who has finished the undergrad training can do those problems without hesitation. Okay, that's our expectation when we are looking for people who can do numerical calculation. But the reality is that it is probably a very high bar of entering the field. So in practice that, well, we are really looking forward to people who can instantaneously tell us what is an eigenvalue problem. You do not need to be very familiar with that, because like if you have been graduated from PhD for like 10 years, you probably won't be able to recall each of the details. But we do expect that you know what it is, and give you like 10 or 20 minutes and to do some revitalization. You can tell me what is the essence of the problem, right? And give you like half a day. You can go find your textbook and to get back the necessary skills for this specific mathematical tool. Okay, so here I want to do a quick introduction or reminder of what it is. For eigenvalue problems, we deal with square matrices. When we say we solve the eigenvalue problem, it is to find the eigenvalue lambda from 1 to n, and n is the rank of the system, as well as the eigenvector. The eigenvectors that can be used to build the eigenvector matrices of that square matrix A. And we want that eigenvector matrix S such that it can diagonalize the original matrix A. And the diagonalized matrix will have the eigenvalue in the diagonal, and everything off diagonal are trivial. Okay, that's our eigenvalue problems. So an eigenvalue is a scalar. It is not a vector. That's why it's called a value. That eigenvector can be found and associated with a specific eigenvector such that A times vector eigenvector equals to eigenvalue times eigenvector. Okay, so it's kind of special, right? So the whole matrix can be represented by a single value. When the second term is the eigenvector, not any vector have this trait. Only eigenvector and its associated eigenvalue have this trait. So they are very special. Okay. So V here is a column vector. Recall that it should be like in a column like this. Each element is lying up in one column. So we have many rows. Okay. When we have a column vector here, we also call it the right eigenvector. Why? Because it is at the right-hand side of our matrix A. So for the same reason, and for the same eigenvector, we can find the left eigenvector. That is actually the row vector. And to recover this equality by having the row vector times the A matrix will be equal to the lambda times U times this left eigenvector. And this edge is a Hermitian because our eigenvector can be complex valued, even though our matrix A can be is real valued. So LAPACK provide DGEEV or GEEV helper to solve the eigenvalue problem. This is our system, and we do not need the right-hand side, right? Because recall that this is the problem we want to solve. We want to find both the eigenvector and the lambda eigenvalue. Okay, so this time we are not just solving the variables. We are finding characteristic vector and value for the system. Then this is the results that we find. You see that we have a real valued matrix A, and it actually generate one real numbered eigenvalue and a pair of complex value eigenvalues. And this pair of eigenvalues are the complex conjugate to each other. And we can find the left eigenvector and right eigenvector simultaneously. Okay, and you see they are different, right? You can use some tools to do the verification. You can also do manual derivation of the system, but that is not very convenient. So I chose to use NumPy and to do the calculation. So first I get the left eigenvector, the real value 1, and I calculate the dot between my left eigenvector and matrix. I got the value here. Then I use the eigenvalue times the eigenvector. I recover the same vector. There is some error, and the error is of around the same precision when I cut off the solution. Because I am using the double precision version, so actually the accuracy of my solution is much better than this. But I'm only printing like 6 digits. This is so that I can save the typeset of my slide, so I can type everything in this page. Then I go with my complex valued eigenvalue and eigenvector. So remember to take complex conjugate, and here complex conjugate, and recover the same complex value eigenvector. Okay, and the third one I'm not repeating because it's just the complex conjugate. And the right eigenvector works the same. I have all this verification in the online note. And there is a helper to do the symmetric matrix. Using a real symmetric square matrix, actually the calculation will be much simpler. And we know it always has real eigenvalues and the associated eigenvectors. So here, oh, forgot to mention about the interface. We still need to specify the row major and column majoring, and all those data buffer and the shape. So as this symmetric interface, SYEV. So, any questions? I probably talked too long. And let me close the poll and see how you are understanding. Okay. So let's take a break of like 3 minutes. We are coming back at 9 o'clock and 7. And during my pause here, let me know if you have any questions. I go to get some water. So if I may not hear you have question, please type in the window. So I'm not seeing any questions, so I'm start to talk. Well, I feel very encouraged that there are 70% of people that still remember what is an eigenvalue problem. That is very good. We interview like maybe like 10 people or 20 people every year, and probably only one or maybe less than one person still remember what is an eigenvalue problem. So in my day job, we usually want to work with people who has been having like at least 3 or 5 years of industry experience. And it's kind of sad that most of the programmers chose to forget about the math after they got into industry. Not everyone is like that, you know, that we guys working in the semiconductor industry always need to keep that in mind. So in my work environment, it is hard to imagine that who can work without, well, who can work on the problems that we want to deliver, and they do not know linear algebra or interpolation or optimization kind of things. We always need to be familiar with or being able to get familiarized with those problems. We usually need to get the necessary tools within like a week and start to program. So of course we will not, it won't be like in an interview saying, hey, you need to record everything you get in like 30 seconds. But we'll give you like maybe 3 hours to pick up what is necessary and to start discuss with people and put together prototypes and start to get things to work. Then we will form some development plan and to purify and strengthen the prototype that we worked out and gradually move that into a product. So I feel that is kind of fun. I don't know if you feel that as well. So let me get back to our lab pack. I want to use maybe 5 or 10 minutes to make it a closure. And we can have some discussions about your project. I hope we have 30 minutes or more to have conversation with you. And it's already 9 a.m. So I believe that you can turn on your video and start to speak without interfering your roommate or anything, right? So if you can, please turn on your video and try to speak as you can. So the next helper is, the next helper should be singular value decomposition. This is to solve for rectangular matrices. So our eigenvalue was to deal with square matrices. But here we want to solve problems that is not square. Rectangular matrix does not have eigenvalue because it is not square. So that you cannot define eigenvalue from it. However, we can define eigenvalue and eigenvectors of it is to time its transpose. Okay. And we will calculate the singular value from those eigenvalues. And this A times A transpose and A transpose times A will give you the same answer. It can be shown, but we will not repeat that. So by using the singular value, we can decompose the matrix A of n column and n rows into U and the sigma and V transpose. So the sigma is the diagonal matrix consists of the singular values. Then we have the eigenvector matrix of A times A transpose and A transpose times A. Okay, that's why it's either way is okay. LabPack provides GESVE, and I have some notes that I want to show you. Okay. Oh, I know what I want to show you here. Let's come back to here, which is have the similar interface as our other LabPack functions, and we need to specify which measuring we are to use, and print the result as U and V. And the verification is much more complex that I do not want to repeat in my slide. So let's coming back to the note. This is the program results, so it can be printed through very long because that data has like 16 by 16. And we can verify our results by plugging all those content back into NumPy. Okay, so we have A and U and V transpose. Okay, so we can do the dot of U times S. S is our sigma single value matrix, and then dot the result of that operation to VT. And you can see you recover pretty much the same matrix with some error, right? There are some error. That is our round off. We cut the round off at the like a 6 or a 7th to the digit. Okay. So we have three singular values here, 11 and 2.4 and 1.3, right? We have three of them. And we can do some experiments, like let's remove the smallest singular value, which is 1.2. Right? Then we can recover our matrix, and the error is like 10%. Recall that our singular value here is 1.2, which is almost like 10% of our logic's leading singular value. So by dropping one, you are not dropping a lot of information, right? And you can drop the largest one, you will see that the result is almost different from your original results. So you are leaving only errors or only imprecisions. And you can do another experiment by removing everything other than the leading one. And your error grows larger, but it is not horrible, right? Well, recall that you only have three singular values. So dropping two out of the three still give you something in around the same order. So that is not too bad. That is not too bad. Okay. So the singular value have a lot of applications, like you can do this kind of analysis for what is the characteristics of your system. Okay. It's super useful in your signal and the data analysis. And the last problem I want to show is the least square regression, that we have the helper GELS here, and this helper is to minimize this problem, so that we need to first formulate our problem into this form. Then we can supply the values that this helper accepts. So there is a rather longer derivation of what the problem is. The least square problem is trying to find a function of the form that can minimize this cost function, which is the square of the is a norm of the square. It's a L2 norm, if I remember correctly. So we need to do this thing where I do not want to repeat them. Sorry about that. You can read it online. But the key is that this is yet another model problem that we can solve using computers. So first, we derive the system, the problem in a way that we know it will be friendly to computer. And then we plug in the number and go into the helpers. Then we can also do the plotting of our results. So those blue bullets are the data points, and the orange line is how we fit using this square for those data input. In real world, you probably will use a lot of data points. And this is a demonstration for just using 4 points. Those are well-established tools. So people know very well about what are the mathematical problems, and as well as how to apply those problems. Okay. Back to your project. It is okay for you to choose to re-implement these linear problems. But it should be more interesting if you find other problems for you to work on, both the definition of the problem as well as the implementation. In this model problem, like least square, we know very well, a lot of people have been working on it, about how to formulate them and how to solve them, and how to write programs to make them fast. But your problem should be more well advanced, more applicable, you can use some real world problems and to try to formulate them in the mathematical form. Then the challenge mainly is how well you understand math and the problem you want to solve, so that you can make the connection. Then you need to connect the mathematics to computer code so that you can solve it using computers. It is often you will find that, you find a problem and you try to solve it using math. Then it is solved. You do not need computers. If a problem can be solved with mathematics, or it can deliver analytical solution, then you do not need numerical solutions anyway, right? Because you have done the hard work to make it math, and it is solved. That's actually the best problem you can get. It is just very unfortunate that you cannot take that into this class, because we want you to practice how to do the numerical software development. So you still need to do the second part. Find a problem that allows you to turn the math into the computer code. And we can write software and run the algorithm or numerical methods. Okay. So in the where is my GitHub? Ouch. Okay. We already have some pull requests. We have newer ones. That's good. We have at least 8 pull requests for your project proposal. So if you can, please turn on your video, and who want to say something about their projects or ideas? Anyone? Okay, I plan to go back to classroom next week. That should help you better about how to express yourself. I know it is particularly difficult for you to staring at the screen and try to say something. Yeah, I know it's challenging. And turning on video will help you because at least you can see yourself. Yeah, someone, please say something about your proposal or your project.
Hello, Professor. Can you hear me?
Yeah, Asma, yeah, I can hear you.
Okay, so perhaps I can share some of my idea, but I'm not sure whether I can do my proposal. What do my proposal say?
Do you already have a proposal written?
Yeah,
or...
it's just a rough structure.
Oh, that's good.
I'm the last one.
Oh, this one. So let
Yes.
me open it up. Actually, you can, if you have your computer open, you can also share your screen. So let me open it up for you. Okay, here is your proposal.
Yes, so actually I'm not precisely sure what this project will have to involve in in numerical method, but I want to solve the problem to optimize FFT. And I think that lots of people in the industry want to solve this problem because it is a very fundamental mathematic method.
Yeah.
And to implement it, there have already been some libraries developed, but maybe I can use the most fundamental way to try to optimize the speed or try to optimize the CPU performance.
Right.
Yes, that's what I think.
Yeah. So actually, in the next lecture, we will talk a little bit about how to do blocking or tiling, right? Most of FFT library that I know are already taking advantage of those cache optimization. Or we can say that most numerical libraries need to take the cache into account. Otherwise, in modern computers, they cannot run fast enough. So this is definitely a great direction to try to write a project that is addressing the performance. Okay, that is for sure. And the fast Fourier transform is well, the algorithm itself is already meant to be fast, and it made some assumptions to make it so it can become fast. Sacrifice some flexibility as well as some accuracy, but it is fast. Okay. There are other Fourier transform algorithms which is not so fast as FFT. Okay, and we do not use them right now because we want the fast implementation. So choosing FFT and computation optimization is definitely a very good direction. Okay, and I would like to ask you, you get this idea that the industry should find this problem interesting. Why do you think in that way?
Because I think lots of people who, for example, like dealing with signal or digital signal, they often need to calculate fast Fourier transport, and if it can speed up their computation, then I think that because time is money.
Yeah.
And also those resources are very important to be organized in a nice way. Yeah, so I think that doing this may help them to calculate FFT in a better way.
Very nice. And I will invite the whole class to chime in when you hear something that interests you. Any question or any comments are good for you to make. Okay, and by following what Asma said about you hearing a lot of people around you are doing FFT, doing signal analysis or processing. And I want to ask further, who are they? What exactly they are doing using CA signal analysis? Do you have concrete statement about what they are doing and what are they?
I only know what kind of industry or what kind of technical compound need to use FFT, like voice processing.
What can help you more is concrete work. Okay, not an abstract description about industry. Like I am saying that I work in semiconductor industry, but it is just a categorical description, right? Because it contains a lot of things. And it probably doesn't make sense for me to explain every detail to you. So that I use a categorical description of that to hide the details. But to help you to understand more about your problem, you need a detail. So the exact people and what they are doing, not the categorical description, but exact work or problems they are solving will help you. And what are they? Can you number one or two of them?
And you mean who are they or?
Yeah, or what they do. What matters more is what they do. But who them are is also a precursor about explaining what they do, right?
For this problem, I'm
Yeah,
not
for
really
the fast Fourier
counting
transform,
that.
or more specifically, the optimization that you are doing, or something associated with them. Oh, let me make an example, and we will come back to your feedback. Okay.
Okay.
So I used to do computational fluid dynamics, and you used to work on a problem that is what we call supersonic jet in crossflow. So I'm all using verbal explanation, so it's probably hard for you to imagine. But this is a key skill in discussion, because a lot of times that you cannot draw whiteboard, like we cannot right now, right?
Yes.
So the supersonic jet in crossflow is to just plug in a jet in which is supersonic into another flow which is also supersonic and see what's happened. Okay, so it is an abstract description, right? But I will give you context about why we do it. It is because that when we want something to fly very, very fast, then we need to add fuel into its engine, right? And that fuel will do chemical reaction to release the heat energy. And that heat energy will go into some reaction and operations to be turned into kinetic energy. After we get the kinetic energy, it becomes the propulsion of that flying object, right? So you know, a flying object is always propelled and propelled by having some jet backwards so that it is moving forward. It is like you are throwing a ball backwards so that, and you stand on a cart, and after you throw in, you move on into the other direction, right? And the airplane or a rocket is working exactly the same, but it is not throwing the ball. It is throwing a lot of gas backwards so that it moves forward. So we need to turn the fuel. The fuel contains energy, right? We make it to to do some chemical reaction and release that chemical energy through heat and going into kinetic energy. Then we get the propulsion. Okay, that's how things are working. Flying objects to fly in the atmospheric. So that's why we do the supersonic jet in crossflow. We want both of the gas to be in supersonic so that we do not need to decelerate the fluid before we do the chemical reaction. And that is an extremely difficult problem. People are solving that for decades. And right now they seem to have a little bit progress, but I haven't tracked it recently. But still, it's kind of interesting because it is difficult, right? So this is an example about discussion. I am describing something I know to you. And estimate you are having a direction of the project, right?
Yes.
So you should know something that we don't know, or most of us don't know. You probably, well, we have like almost 30 people. So probably some among us knew what your problem is, but we don't know who they are, right? So you should say something about the detail about your problem. So somebody could probably echo and give comments to you.
Okay.
Yeah. So again, back to the question, what is the specific applications or use for the problem that you want to develop with?
Because I'm not the expert, but I can briefly describe how voice processing works.
Yeah.
Okay, so when dealing with voice effect, people need to analyze the wave of the voice, and there are also categories. And when you are trying to change the effect of the voice, or you want to pick up some specific distinction from part of the noise, part of the voice, then you will need to like split apart some of the materials from the voice, so that when doing that, you will need the FFT to help you to sort out the voices, the signal. Yes, and when the length of the voice is very long, then it will be very time consuming, and it will take a lot of the resources from computer or server. So that is the reason why optimizing FFT performance is very important.
Yeah. So you mentioned a specific analysis for audio signal, right?
Yes.
Does that imply that you will use that kind of signal for optimizing your algorithm?
For now, I think I will try to implement the performance metrics by randomly put some signal into a function and compare the results between my tools and the normal library.
Mm-hmm.
Yes.
Yeah. So not a specific type of signal, not that specific audio signal,
yes.
but you are thinking about something more generic.
Yes.
Right. So you talked about using randomly generated signal. Then how do you know that signal has the characteristics that you want?
And you mean how do I pick out this?
No. Randomly generated signal still have some characteristics.
Yes.
Yeah. And how do you know the characteristics of your generated signal? It's what you want to test or apply for. And do you know there is a special types of numerical algorithm that is used for generating the pseudo random number?
You mean that in language or?
Not specific to language, but in computer there is not a real random number, right?
Yes.
If you are disconnected, right, from the network, if you are connected to the network, you can use the network to make it more real. But if you are not on the network, then you do not have the real pseudo number. sorry, random number. So your random number in computer is always what we call pseudo random number. They are not real random number, but something generated from an algorithm.
Yes.
Yeah. So that kind of thing will have certain traits, certain characteristics. They are not truly random. So how are you going to make those characteristics to serve for your signal? Because your signal will extract those kind of characteristics, right?
Yes.
Yeah. So Esme, probably you didn't know about the pseudo random number generator, and that is fine. And it is also fine for not being an expert about the topic you want to do. It's perfectly okay. Okay. Well, if you are in a course or some training for like a specific numerical algorithm, then after the training or before the training, you should be an expert about that, right? So when people are asking you questions, you should be able to answer per your expertise. Okay. That means you spend a lot of time on that subject. Then you can become an expert. Yeah, that probably means 5 years or 10 years, something like that. But this is not that kind of course. So actually what I am asking the class is that to work on problems that you are not experts in. And well, you cannot become an expert by taking a course of a semester, right? That's impossible. If you can become an expert within like half a year, then that subject probably isn't very, very difficult, right? Okay, so no worry about misunderstandings and insufficient knowledge about the subject. Okay, we probably need to overcome that mental obstacle before we can do effective discussions. And Esme, you are doing a great job. It's great to have the conversation with you. Yeah, thank you. It's and anyone has other, including Esme. Do you have follow-up thoughts about what I said? What do you think, or what Esme has mentioned? I recall that I have reviewed another proposal that has something about audio analysis, but I cannot recall which one it is. Yeah, if you are here, do you want to say something? And everyone can say anything.
Professor.
Hey, Jonathan.
I got a question here. Like, I think it might be a stupid question, but I'm wondering, like, if this proposal is necessary to be something related to numerical science or anything else.
Usually it will be about some sort of science, but it doesn't need to. You can select a topic as long as you can practice the skill that we have covered, and we will cover in the later lectures. That will be fine. The point is for you to do practices.
Oh, okay. Yeah, got it. Thank you.
Yeah. So, and I think, Jonathan, you made a great point that whether or not it needs to be well, my interpretation is a hard science. No, no. Writing code is difficult enough. You can get inspiration from the so-called hard science for your project, but it doesn't need to be so hard. Okay, let's focus on code development. Analysis of the problems will be important for you to do your implementation. So let me follow up with you, Jonathan. What kind of hard science do you have in mind for projects you probably want to do?
The reason why I asked this question is actually because the field I'm studying, especially for my graduate project right now, I'm not actually focusing on something related to numerical science. So, but I'm not actually focusing on computer vision. But actually, these two fields don't have actual relations. So I'm just wondering, if I can make some projects related to computer science, but also got some relations with the field of numerical science. But I'm still now brainstorming, so actually don't have any actual ideas.
Yeah, that's good. Computer vision does incur a lot of numerical calculations, right? It's just a matter of fact.
Yeah.
So you are able to do a lot of practices, which is the point, right? It's okay if you are not discovering a new atom for your computer vision part. It's definitely okay. And I'm very happy that you bring up these ideas, and you all should try to bring ideas like this and to confirm whether or not it is what we want to practice. So yeah, if you have a specific problem in computer vision you want to solve, and that probably is very suitable for the term project. You don't need to make it super big. I like to say to people that if we are trying to build a platform for something, that usually decide that we do not know what we want to do. So that we have to do a platform before we can solve a real problem, right? So that applies to my feedback to Asma about what specific problems or people or their work that you are looking at. It is okay for us to make general tools, but in the end of the day, we need to work out something that is testable, right? Making software requires us to write something that can be verified. Otherwise, we are just playing sense. And
yeah, exactly.
Yeah, we won't have, well, software is already a very, very superficial, very flexible. And if we do not have something clamped to its framework, it's very difficult for us to trust what we make. Yeah. And I guess computer vision probably is a very, very popular topic. Yes. Probably many people will do that.
Okay, I will think more about it. Thank you.
Yeah, that's good. And I do have a specific framework for your proposal, right? You do not need to follow exactly to the framework, but I will discuss with you according to the framework. That makes my life easier. But you can have strong opinions. Okay. And okay. I like your strong opinions. That means you need to spend a lot of time in writing up your opinions. So I'm not saying I require you to do that. But either way is okay. You can use the framework, or you can try to disassemble that framework. It's all good.
Okay, thank you.
Yeah, thank you. As I think we are getting better and better. And I hope every one of us to have conversations like this. And I will be more and more critical in the discussions. The critical back and forth in discussions is the key for you to understand something that you don't know, especially in the practicing of code development. We oftentimes got our mind widened in the problem we want to solve and cannot get outside of it. If you want to think outside the box, then you really need a group of people who attack your ideas, that make you think what is missing in that. And I know this takes a lot of practices. Okay, so let's meet in face-to-face next week. And I can spend less time in my lecture and have more time to discuss with you. Okay. When I can see you, I promise you I will perform much better. Any other questions you want to ask or you want to express for yourself? All right. I got a question from Bowie in the chat window. When it comes to absolute correctness versus speed, in which way would the microsolver tend to do? Like a naive way of calculate the norm can lead to overflow, but Hypod uses a slow implementation that does not overflow. Which libraries like that make the same decision? That's an excellent question. When you are in the choice between correctness and efficiency, there is an answer, which is there's no answer. No, there is not an absolute guideline about whether or not you go to correctness or you go to speed. That is why I like to write commercial code more than academic code. In academic or research code, the gauge between correctness and performance is very vague. It is almost all up to you. No matter whatever you want is okay, as long as you can write a paper, right? So there's no standard. But in commercial code, we have a very good gauge called money. If you can get your tool to sell, then that is the right balance, or an okay balance between accuracy and performance. If your users can tolerate that kind of accuracy, you need to be absolutely honest to your users, of course. Telling them in what scenarios that you have certain kind of accuracy, then they will ask you, they will make requests to you for what they want, and they pay you back in real money, right? So you know they are serious about what they want. Then you work out what you promised, and you keep thinking for your users what they also want, because a lot of times that they do not know exactly what they need. Then it still becomes case by case. So our the answer is still that no, there is no answer, but you use the gauges, no matter it is your conscious or your hunch feelings for whether or not you can write a paper, or you use your collaboration with your users to know what is their precision demand and their performance demand. A lot of times that they are negotiable. If you say, hey, to get the absolutely correct answer for this part, you need to pay, say, like 100 servers for 10 days. And they will say, oh, wow, that is too expensive for the use. Then can you make it faster? I can tolerate some inaccuracy. Then you work out a new balance for them. Yeah. So Bowie, I would be interested in what problems you have in mind for this question. It is, to me, it still seems to be related to a proposal, right? Because that will determine, that kind of balance will determine how you are going to architect your software. How are you going to put together? What is the core of your system? If you shoot for speed, then accuracy probably will be a secondary consideration, at least for some part. And that matters for different problems. I would be interested in learning what you are thinking. Yeah. You don't have to answer me right now, but we can keep talking, maybe with your proposal in GitHub, or we can have other scenarios for discussions. Okay, so the time is up. I won't want to hold you for too long. So let me know if you want to have further discussions, and hope you have a great day of the rest of your today. Thank you very much. Let's see you next time in person in the classroom. Bye-bye.
Thank you.